Nice to meet you. This video contains information about Proteus, which allows you to test firmware without a kit. You can check the results by applying many of the firmware codes I provide to the virtual environment from the Proteus design file, as you can see. Let's take a look at the main design contents discussed in this video. First, ATmega 128 was adopted as the basic MCU. LED. Xtal, this is crystal. We will explain the design files for the reset and power buttons. We create an environment for LCD, buzzer, ADC, DC motors, and RS232 communication. I will allow you to practice many of the firmware in this channel that I explain in this virtual environment. Then, we will first explain the content that will be attached to the video you watched. Proteus for AngelRo is the actual final result of Proteus. The Proteus file, corresponding to the image file shown just before, in the Proteus for AngelRo folder. The Proteus for AngelRo.pdsbrj file is provided as is. The file in the SRC folder contains an image of the design file shown earlier, and this image file is also provided. Next, we provided you with a summary text file for using Proteus and test codes for each unit design. That should be tested during the actual design process. If you would like to follow me and create the same result as this design, please download it from the link provided in the description of this video. From now on, I will show you the actual design and testing using Proteus. When you run Proteus, you will encounter this environment for the first time. This is the home page. Here, you need to create a new project. Go to File and click New Project. The path where the project will be saved is set in the path field. You can edit the path by pressing the browser button. I created a folder called Proteus. Under Work on Local Disk C, we're going to select the folder here. The project name here will be Proteus 5. Then I'll click Next. Select the Create schematic for the selected template option. Set default, and then click Next. Then I'll click No Firmware Project. If you click Create Firmware Project, you will set the family, controller, and compiler you want. To obtain, create firmware in the development environment provided by Proteus and test it. However, since we will be practicing the project using CodeVision AVR and Microchip Studio results and hexa files, you can proceed by checking No Firmware Project. Let's click Next. Then you will see a summary of your project. It says that we only make schematics. Here, you can see the part where the PCB is made. But that part is not shown because the version of Proteus that we have obtained and that I have licensed is only simulation software. There may be times when you ask if you would like to manufacture a PCB. In that case, you must not select it. So, you can create a project that just creates schematics. I will click Finish. This is the first time you will encounter a development environment like this. First, let's do some initialization. The first thing to do is enter the system. Come to the system and go to System Settings. First, check whether the library local part is European, and proceed as is. Please be aware. Next, come to the template and there is a set junction.style. Change the size to 30. Choose a round shape. Just keep it as is. Next, we will set the color. If you come to the template, you can come to Set Design Colors, and there are paper colors within colors. I will change the paper color to white. And I will keep the settings for Show Hidden Text and Show Hidden Pins as is. Let's press OK. Lastly, let's modify a few shortcut keys. Come to the system. After entering the set keyboard mappings, go to the command group and press the letter O. Next, rotate clockwise. I already changed this part to R, but you will see number minus. Come to this part, press the R key, and click Assign. If I press Q, it changes. Just click Assign. Come back, and press the R key and click Assign. Next, you will also change the X mirror to A. I'll change it to A, and then back to M. You can do this by pressing M and Assign. In this way, you can change rotate clockwise to R and X mirror to M. Please click OK. Now that we've made it this far, we've completed some basic settings. To give a simple explanation of Proteus, you first need to add objects to your design. For this, you can see the component mode here. Go to component mode. Just below the arrow, go to component mode and press P. So, if you want to add ATmega 128 here, search for Mega 128, and you will see the results here. Select ATmega 128, this part here. If you are designing a PCB, you should check the footprint information and make an accurate decision before registering. However, since we will not be doing artwork for PCB production, we will ignore it and proceed with most of the designs. Just click OK. Then, the shape of the mouse changed to a pencil shape. If you click once, the object will appear pink, like this. If you place it in the center and click, an object will be added. Now at this point, let us give some explanation. If you look now, there is a toggle grid as you can see in the top toolbar. So, when you use a grid, you will encounter 3 types of grid: environments, checkerboard, dotted, and invisible. Zoom in and out. This is zoom in function. This is the zoom out function. The next step is to zoom in on a specific area. If you zoom in like this, when zooming in on a specific area, you can see it enlarge this much. Once. The third magnifying glass button here to go to zoom to view entire sheet so that you can see all the objects you are designing at once. You will see them all like this. Next I will explain the toolbars on the left side one by one as I practice with you. From now on, we will register actual objects register devices, and proceed with the design, starting with the LED. For LED design, please first go to Terminal Mode here. Terminal Mode. Let's go to Terminal Mode and register power and ground one by one. I will register 1 power and then 1 ground. After registering at this place, you need power and ground. Then, using the selection tool, double-click to register the VCC here. So, let's change the string and the object string to VCC. When I get to this point, I put the image file aside. We will design the LED part first. When designing an LED, if you are going to connect numbers 0 to 7 to each ATmega 128 porta, it may seem very complicated if you connect it with a wire. So first, we will zoom in on porta, which is the part to be designed as an LED part. Let's zoom in. Zoom in on the porta section and come to the terminal first. Come to the terminal. Select default. And then add 1 here. Add 1 to porta. Then select the object and click Copy to Clipboard. Copy to Clipboard to copy it. So, when you double-click, you can copy to clipboard like this. And then when you do copy to clipboard, right-click and select Paste from Clipboard. The ones I chose just now are displayed as they are because you set default in the terminal. So numbers 1 to 4 are displayed as is. When copying, right-click and select Paste from Clipboard. So since we have to design a total of 8 LEDs, we created a terminal to make 8 terminals as default under the terminal so that they can be connected logically without actually designing the wires that can be connected. Even if you double-click it, you can connect even if you double-click it in the terminal. Even if you connect it like this with a pencil, the wire will be connected. Next we will enter the label information into the terminal. We will input LED 0 through LED 7. I will enter LED 2 sequentially. LED 3, LED 4. And so on. If you press Ctrl Z, the information you just entered will be cancelled. These will be LED 5, LED 6 and LED 7. Then we need to come to the left and design the LED again and connect it. So, I'm going to put one here as default. After selecting it, press R to rotate it. Then, you can enter LED 0 here. After canceling the input with Ctrl Z, go back and double-click to enter. You can register the string by clicking directly on the label, information that has already been registered in the string combo. Selecting it like this and clicking OK. Since you entered 8 labels for the LEDs on the ATmega 128 side, they will be automatically loaded and displayed on this side. What information do you need next? This time we need to register the resistor and the LED. Come back again. This time to component mode. If you press P and click Pick Device, you will see an environment where you can register objects and devices as shown below. What should you input here? If you type residential and then press enter, you can see many resistance-related elements as you can see. If you double-click the RES device generic resistor symbol, here you can register it in this quick device window. It's called RES. Next, we will register the LED. If you change the keyword to LED, enter -, and then enter A, you will see LED Aqua active. Animated LED model. If you click this, even the LED will be registered. Please confirm. First, let's take an LED and place it. And I'm going to take a resistor and I'm going to take a resistor and I'm going to put it here. In this state, you can enter select mode. Select the LED. And then use the rotation function, R, to rotate the LED. Then, you can add a resistor over here. I'll put like this. Since the resistance is a resistance without polarity, it is expressed as. You can see here. LEDs are importantly polarized. If you look now, P+ direction is on the MCU side. That's why you need to rotate it 180 degrees. You need to rotate it this way and understand the polarity accurately. So, as you can see, the left side will be the positive polarity. And when we design LEDs, we will use the anode comma method. When power is supplied from the outside and connected to the processor through the LED, the MCU will proceed with a design method in which the value of port must be set to ground or 0 to create a potential difference, and the LED will turn on. If you have made it this far, we can now connect using wire. If you have made it this far, you have already designed a single LED. What you need to pay attention to here is that the resistance value is 10K. You must change the 10K capacitance to 330 ohms instead of 10K for voltage distribution to occur and the LED to light up. If you set it to 10K, it may be difficult to check the LED turning on because only a very small amount of current is simulated to flow through the LED. In this way, we design one. We have one design now, but how many do we need in total? You need 8 LEDs. So from now on, we will make 8. When making 8, we will use the block copy function to copy them and design them accordingly. Please zoom in appropriately. When you select this amount and zoom in or out, you can easily use the mouse wheel to zoom in and out by placing the center point of the mouse. Select this much with your mouse. Right-click. And then click Block Copy. Then, how many in total do you have? If you add 7, it becomes 8. So 1, 2, 3, 4, 5, 6, 7. And 8 were copied using block copy. After that, just add the wire. So let the ground move. A short circuit may occur. So, we will connect the wires using a wire design tool. Once you have a pencil, you can select it and design it using anode common. If you make it this far, it looks like the LED design has been completed. Then, to confirm that this is the LED part, if you look here, there is a graphic object with the letter A written on it. 2D graphics text mode. Let's press A to add text here. In component state, enter LED here. Let's set the height value to 0.2. Let's go with 0.2 inches. Let's click OK. It has become LED by going back into select object mode and moving it to the center and placing it in a place. That looks good. The LED design has been completed. Since the LED is located a little higher than the original location where it was designed when lowering it as a whole, select this amount by dragging with the mouse. You can select it and go down like this. You can lower it a little like this. You can adjust the position slightly higher so that it does not overlap with other designs. Next, click Zoom to view entire sheet to see the entire page, and it will enlarge like this. This time, we will design the Xtal part. When designing the crystal part, we will also use terminals to establish connection relationships. Go to terminal mode, select default. Then, create a terminal in the Xtal section. And connect. Next, let's enter the label information as Xtal1 in the terminal. Next, let's enter Xtal2. We need to design Xtal in this area. Xtal requires crystals and capacitors without polarity to be registered. So, come to component mode and press P. This time, we need to register the capacitor. So there are two types of capacitors. There are polarized and non-polarized ones. Click on the capacitor. Select Device Generic Non-Electrolytic Capacitor and click on it. Next, let's press CAP pole again, this time to register a capacitor with polarity. Then, you can see the polarized capacitor. Please click to register. I'm sorry. Next, enter the crystal. Here. To register it. So, it says crystal. Device, quartz crystal. Let's double-click this part to register. Next, we will register the switch we will use next. When registering a switch, we will search for button here. As you can see, when you press the button, there is an active SPSD push button. Double-click here to register. If you have reached this point, the graphic object devices for designing buttons have been registered. Then, we will design the crystal first. Click on Xtal. Put away. Next, let's put two non-polarized capacitors here. Let's put two of them. Then, you should go to terminal mode and put the two default values here. I'll put two of them like this. Zoom in and go in. After switching to selection mode, select it and press R to change direction each. And for the label information, you should select XTL1 here. Select XTL1 from the combo, and OK. Again, let's select XTL2 here and click OK. Then, the ground has to go here. So, in order to select the ground, we will move the existing registered ground this much. Let's use selection mode to move over here and select here. Then, before designing through the wire, the direction of the crystal must also be rotated. Please do it. And the capacity value must also be determined, since the capacitor is equipped with a capacitance of 18 to 22 picofarad. We will modify capacity value here by setting it to 20 picofarad. 20 picofarad. The datasheet will say to use 18 to 22 picofarad. From now on, we will design using wires. I need to move it up one notch. Do it like this. By doing this, the crystal was also designed. Then, if you select the LED object to copy, and then right-click, copy to clipboard will appear. If you move here, and right-click, use paste from clipboard. One here. I will edit the content here and say XTL. Please just change the letters. Then, it will be corrected. This time, let's design the side part. You will design the reset part on the side. First you need a VCC. Right-click on the VCC and select copy to clipboard. Then come here and select paste from clipboard to place a VCC. We need to design in this area. And you need a 1K resistor. So, let's add a resistor. Next you need a polarized capacitor. I'll bring one over here. And you need a switch. Let me press the button and place it here. And because we need a ground, select the ground, right-click, and select copy to clipboard. Come here. And use paste from clipboard to register one ground. First, you need to rotate the resistance. I change it. Look closely at the polarity of the capacitor through R. As you can see the polarity. If you look at it now, the straight line will be positive. Where there is a straight line, it becomes a plus. Please move VCC upward. We will also move the resistance. And move the switch down. As you can see, when you move the switch becomes pressed. To prepare for this, when you right-click, there is a drag object. Let me move it a little. By dragging the object, and the ground is placed below. This side, so it may be difficult for the wire to pass through. So, let's move the crystal again. Please move the crystal again. Then, select all the objects. Select these objects. And select the object again. Let's move. So, after moving this a little, we will proceed with the design of the wire. If you look at it now, because there is this object, it is bent. So, let's move a little further. Do it. After moving, you must select the selection mode. Select the object and then delete it. To erase it, the mode will now change to pencil again. If it changes, please design the wire like this. I need to lower this part further to make it look better. If you select an already designed object and move it like this, you can adjust its shape to become a right angle. If we get to this point, the reset part using the switch are completed. But we need to change the capacity value. 1K is set here. And the capacitor value is 0.1 microfarad. So, here goes 0.1 microfarad. 0.1 microfarad. And let's go into Edit Properties and change the part value here to SW1. Please change the part reference SW1 to SW1. We will reset the part value. If you do it like this, it will look like the image I provided. So, since clicking doesn't work, whenever you edit a switch, right-click after accessing it, and use Edit Properties, or Drag Object. Please be aware that we utilize these two features. Next, we will design the power part. You should also record reset here. Also, select the LED, right-click, and then select Copy to Clipboard. Come here, and use Paste from Clipboard and place it here. Double-click, and go in and write what we want here. I will record it as reset. Now, the design of the reset part has been completed. To know that the processor is powered, let's briefly design the power section. After selecting VCC, copy to clipboard, and then using Paste from Clipboard to place it here. And copy the LED, which is a type of diode and resistor. So, select a resistor and click on it. Then click Copy to Clipboard. And then copy it through Paste from Clipboard. Next, let's add an LED. To copy, this time, select the registered device. It is located here. Then we need to get the ground. Right-click. And select Copy to Clipboard. And paste from Clipboard. After zooming in, we will connect the wires. The resistance value needs to be modified here as well. You need to change the resistance value to 330 ohms instead of 1K. Now let's design a button this time. Let's design a button. After moving to this part, in order to input the button, add 3 resistors that are already registered. I'm going to put 3 resistors here. Let's take one, then I'll put another one here. And let me bring the third. I need to move around a bit. Position. It's slightly around this area. Next we will place 3 switches. Click the button and place 1, 2. And 3. Next, we need to copy VCC and ground one by one. So, select VCC, right-click and select Copy to Clipboard. Wait a minute. Right-click and Copy to Clipboard. Go here, right-click, paste from Clipboard, and copy one. Then we need to copy the ground. After selecting it, right-click and select Copy to Clipboard. Then go to the right and select Paste from Clipboard. You should use Paste from Clipboard. I'll copy it for you. Next, you must also bring the port. The port must also be registered. Before registering the port here, we will make sure that the port is registered on the processor side. We will have terminals on PORTD4, interrupt 0, 1 and 2, and buttons 1, 2, and 3, respectively. Place 1, 2, and 3 here. Through terminal defaults, you can go to object selection mode, right-click, and rotate clockwise. You can also type R on your keyboard. Let's select R. R. And then connect the wires. Here's a button. Let's call it button 1. It's called button 2. Let's call it button 3. Let's select these objects and do a block copy again. Select these objects. Press Ctrl+C, copy the block. Move it. And release it with ESC. To deselect, just press ESC. So bring it over here and place it around here. We will also move button number 2. Put here. I'll put number 3 here. After we get to this point, we will do the rotation first. VCC also needs to be rotated, so rotate it using the R key and also rotate button 1. Please rotate button 2, and then button 3. After editing up to this point, the layout is somewhat complete. From now on, we will connect the wires. Do this first. Please do it. please do it. And then, after doing this, do it like this. And then, do it like this. If you do this, and then the wire is connected to the front part, I will connect to ground. If you work up to this point, it seems like it was edited well. So, the resistance value is 10K. All you have to do is add a 10K resistor. I will save it as the default value. The connection to PRTD is now complete through the terminal. It seems that the electrical flow was designed appropriately. Lastly, in order to add graphic content to the button, select Reset and select Copy to Clipboard. Come here and copy it using Paste from Clipboard. Then, double-click Reset and change the term here to Button. I'll press OK. So let's stop here. Next, what you need to do is design the programming. Enable part, pen part. It would be better to register PN. So all you have to do is design VCC and resistor here. So, to make another copy of the VCC, right-click and use Copy to Clipboard. And paste from Clipboard to bring it here. Next, let's bring in a resistor as well. Let's select one resistor, RES, and place it here by enlarging it. Move. When you connect wires, you can select device, objects, touch them, and then stretch them like this, and the wires will be automatically connected. You can connect wires in a pencil shape like this. But as you can see, please know that there is also a way to connect wires through contact between graphic objects, same as OrCAD. Now at this point, the Proteus design file that can be used to experiment with the first firmware has been completed. So, since the LED and button have been designed, if the normal design has been completed, you can run the firmware. In order to run the firmware, you can already create your own Code Vision project. Through other videos, I have already created a Code Vision AVR project for ATmega 128. If you look at the Proteus AngelRo test SRC file I provide, you will see a code called LED and button test. At the end, we will select this area, copy it as is, and then compile it. You can come and build the project. There are no bugs. If you look here, you can click the Build All Project File button, or press Ctrl F9 as a shortcut key to compile, like this. Okay, so you should know the path to this file. You must know the project path you created. Let's proceed with running the firmware. You can also select ATmega 128 and double-click. You can also select ATmega 128, right-click, and select Edit Properties. After right-clicking, here is where you can select Program Files. There is a box to choose from. Before that, you must first select the internal 1 MHz as the external clock through the Xtal fuse bit and modify the clock frequency to 16 million. Then, you have to go to Program Files and click the button to find it. So I have an x1.hex file under C drive work under HW3_CV under EX1 debug. So, just select this file, and then I'll press OK. Now, let's try running it in this state. Then it goes like this. If you press the button once, it will respond. It's not responding. There was a bug. There was a bug, as you can see right now. When I connect the LED, I copied it and did not modify the LED label. If you want to cancel the simulator, just press the stop button at the bottom here. Yes. Click to change this to LED 1. Please change to LED number 2. Please change to LED 3. When copying, there may be some parts that are omitted. Let's change it to numbers 5, 6, and 7. In this state, a bug occurred due to the structure in which all wires were previously connected to number 0 of Porta, but now each LED is connected. If you look at the code, if 0 is pressed on PND, the AA pattern will be 55. If 1 is pressed on PIND, then FF will turn off all LEDs. Let's try running it. Then AA will be output. 55 will be the output. All outputs will be OFF. So, please quit the simulator. There's a great tool that allows you to see electrical flow visually, and I'll show you how to set it up. You come to the system. After going to Set Animation option, click on Show Wire Voltage by colors and show wire current with arrows and then run it. Now, if you press the button in this state, you can see the electric flow. And if you press it again, you can check the electrical flow, like this. So, when you simulate, it is best to be sure to modify the Set Animation option. Now, we have completed the design of the LED and button. And now, I have to move on to LCD. Since we have come this far, we now need to design the LCD here. The LCD will be connected to PRTC. We connect the LCD to PRTC. So let's start with Porks terminal. We will expand to PRTC. Go to PRTC and select terminal. Select a label and do it 1, 2, 3. Port number 3 is not used. Go to pin 4 of PRTC and do 1, 2, 3, 4. So, what we are going to write here is that we are RS. After that, I'll just put RW here, and enable here. Then, when you do DB4, DB5, DB6, DB7. All the parts to control the LCD are done on the microprocessor side. We will connect it with wire. At PRTC, we are designing LCD. I designed ports LCD. In this part, we will implement the LCD. To implement an LCD, you must first register the LCD and variable resistor. So come back to your device. If you look here, we will come to component mode and select the device. Let's click Pick Devices and say something here. This time, we will select VAR RES. Then, you won't see it like this. In that case, if I were to just type something here, I would type pot. When you say pot, you will see a pot, an active type variable resistor. Please click to register. Next, what you input for the LCD here is LM016L. If you input only up to 016, you will see the LM016L display 16 by 2 alphanumeric LCD. So I'm going to click OK. So first, let's get an LCD. Let's bring an LCD. Move it this way. To move it, we will design the terminal at the bottom here first. Go into terminal mode. Select one. In default. Then right-click and use rotate. Clockwise, RR2. Rotate. After that, select it. Right-click. Copy to clipboard. Right-click. And then paste from clipboard. Paste from clipboard. Paste from clipboard. Then we'll duplice from clipboard. Paste from clipboard. Paste from clipboard. Please connect first. After pressing ESC, you should now go to the default selection mode and change it here below. Or, you can select one registered below from the combo. Please select from below. And this is RW. After that, when we get to the enable stage, it's basically about the LCD. Now we will proceed with the circuit design. For the power supply VSS, VDD, and VE. Oh, I missed it here. I have to change it to 4 or 5 again. If you don't connect it, you won't be able to control the LCD. Change it to 4. And here, I will change it to 5, DB5, DB6, and DB7. I need to change DB7, not LED. If we do this, They will be connected to each other, logically. Then we will design the power part. First, you need to copy VCC and ground one by one. Go to the full view. Select one, right-click. Copy to clipboard. And then paste from clipboard. To import one, I'll have to bring a ground and then a VCC. Click Copy to clipboard. And paste from clipboard to copy. I'll bring it to you. Let's zoom in. It has to rotate. I'll give it a rotate, like this. Please rotate. Next, we need to get a variable resistor. We came to component mode and registered the variable resistor, which we call pot. So I'm going to make a pot and put one here. And we will rotate it using rotate. After moving to selection mode, select everything and press R to rotate it. Let's zoom out to make the selection easier. If you do this, you will need one more ground. Select it, right-click. Copy to clipboard. Paste from clipboard. Move it here and register one. Now, if you have made it this far, you have registered the necessary objects. We'll move around a bit. The design can only be completed if we move this far. Let's do it like this and connect the wires. First, the part that expresses the VE intensity must be connected to a variable resistor, so connect it like this. Just connect the ground part of the variable resistor and connect the power part to the variable resistor part. Also, do this because 5 volts is supplied to VDD. VSS needs to be grounded. If you do this, it seems like it was designed. Since the variable resistor needs to be 5K in order to change the capacity value, I will grab 1K, double-click it, and then edit it to 5K. When editing the capacity value, select 5K, double-click it, and then edit it. Like this. And when you move this, label part reference, called RV1, you can also select it and move it, like this, to place it where you want. Well, if you make it this far, the LCD part has been designed. Let's assume it's an LCD and add a graphic object. Select the LED, right-click, and then select Copy to Clipboard. I'll paste from clipboard and copy it here. Let's press it to change it to LCD. Now, the LCD part has been designed. To check whether the LCD is well designed, we will insert a test code and check. Please open Code Vision. I will get the code from the test source I provided. I will erase the entire thing and overwrite it, because once again the comments are missing, because you're a little confused. If you press Control A and then Control V, you will see the LCD test. There's one thing you should be careful of. when I download it to the kit. I don't do it with code like this, but if you go to Configure in the project, it's in the C compiler. If you go to Libraries and go to alphanumeric LCD, you will see Enable alphanumeric LCD support. You must uncheck this part. I check this and change it to PoRTC, then changed everything to PoRTC and then practiced. If you are using Proteus, this alphanumeric LCD will not work. Now you need to uncheck it. Uncheck it, press OK. And then define the LCD port as an assembly command. So PoRTC is at address 0x15. So you need to set up the LCD port using assembly commands. Next, you need to add the lcd.header file instead of the alt.header file. Then you can use the same LCD command. Then let's compile this and see if the LCD works well. I'm going to press the Ctrl F9 button. Cancel. If you right-click on the microprocessor and go to Edit Properties, you will see the same existing hexa file. So, please make your choice again. Normally, once selected here, the newly overwritten hexa file will be loaded. But if it does not run properly, please be sure to click on the hexa file again to select it. Let's run it. Then Geo 1004 I love you. It looks like this. I will stop. At this point, we have completed the design of the LCD. Now, let's design the buzzer part. The buzzer part is connected to OC0 and PoRTB here at number 4 to implement the buzzer. So let's register the terminal first. Let's put the terminal here. And label it buzzer. The label is buzzer. Please use the label buzzer, buzzer. Buzzer will be implemented at the bottom here. We will implement this part. First, get a terminal. Next, to implement the buzzer, you need a resistor, a speaker, and a transistor. Let's register a new device object. What you input here is when you input the speaker. When you input speaker, speaker. As you can see, there is speaker, active, loudspeaker, loudspeaker model analog. After selecting this, I will confirm and double-click. Then, if you enter only 2SC1815, 2SC. For the transistor, you will see a total of 5 objects, devices. Then, all you have to do is click on 2SC1815. Please click OK. First, we need to get a resistor. Put a polarity resistor here. Then I'll bring in the TR. 2SC1815, please bring it. Then, there needs to be a ground as well. So, select the ground, right-click, select, copy to clipboard. And then, paste from clipboard. I'll put it down at the bottom. Since the speaker needs to be input, we will position it like this and register the speaker. This time, we will select a speaker and register it here. Select it, and press R. To rotate it. Then, you need a VCC, so let's bring in VCC. I'll copy to clipboard. Paste from clipboard and put it here. Select it and press R to rotate it. Once we get to this point, the design part is complete. You can come down one more time. Let's move around a bit. I haven't adjusted the capacity value yet. If you look at R15, you should change this part to 5K instead of 10K. Next, we haven't entered buzzer yet in the terminal, so you need to enter buzzer here. Buzzer. Okay. Once we get to this point, we have designed the buzzer part. This became part of the design for buzzer. Then, I will copy a graphic object and record it as buzzer. It said buzzer and there is buzzer. Now, let's check whether buzzer is working well. Please open Code Vision and import the buzzer part from the test code I provide. I'll copy the buzzer part. All you have to do is make a copy of this amount. To compile the buzzer test, let's press Ctrl F9. This time, the hexa file will have been overwritten with the existing hexa file. Let's double-click here and run it without selecting the hexa file. I tried playing the phone ringtone through buzzer. This concludes the testing of buzzer. Now, there are 3 things left: ADC, RS232, and motor. First, let's do the motor. In order to operate the motor, 2 devices must be added. Requires L293D and DC motor. So, let's register that part first. Come to your device. Go to component mode. Click on Pick Device. And add something here. If you say DC motor, it will look like this. If you see a DC motor, what do you do here? DC motor, active, simple DC motor model. Double-click to register the motor. Next, you need to register the motor driver. Let's enter L293. When you press L293, the device L293D up to D is selected. Double-click to register one and click OK. And then, I'm going to click on L293D and place it here. Bring L293D here. At this point, I'll put it here. Please bring it in, and we will register 2 motors. I'm going to put 1 motor like this, and 1 over here. If you connect the motor first, zoom in and connect the motor. Like this. Then, we need VCC and plus 12E. First, you need a VCC, so select the VCC, right-click, copy to clipboard, and paste from clipboard. Then, bring up 1 power in terminal mode. To register VCC, let me add some power here. Like this. You need 4 terminals. I'll have to get 4 of them, so I'm going to put the 4 default terminals here. Bring 1, 2, 3, 4. Next. This time, I'll select it. Right-click and rotate. Let's press R like this to rotate. Then, I'll move it up a bit. Since plus 12E goes into pin 8 here. It is expressed 12 volt. Then, we will connect. Then do this. On each side. 5 volts should be enabled. Originally, you could implement the enable function by designing a pin. Basically, in order to save pins. AngelRo adopt the BA6208. So the 6208 does not have a structure in which the enable pin can be controlled by the processor. Therefore, you can understand that the enable pin was artificially inserted. I couldn't find BA6208 in Proteus. So, please be aware that it uses L293D. Copy to clipboard and move it here. Please attach them, one by one, and connect them. Next we need to put a label in this terminal. What label do you put in the terminal? Here it will be motor_gray. motor_B. And then, here will be motor_A2. motor_B. In this way, we must clearly define the 4 terminals of the microprocessor. I can't see the text clearly. Please select this much. Let me move it a little bit. I'm going to move it, and I'm going to move this a little bit as well. Now that we're done with this, shall we move this a little bit as well, to this location, because they clash with each other. Once you've made it this far, the location has been decided, so please adjust it so that it does not overlap with other objects. You can do it like this. So finally, let's add a DC motors graphic object here and connect the terminal to the microprocessor. Right-click and select Copy to Clipboard. Then right-click and select Paste from Clipboard to copy it. I'll bring it here as DC motor. Let's enter. DC motor. Here, it's called DC motor. When controlling a DC motor, we connect it to 4 compare match output ports, OC1A, OC1B, OC1C, and OC3A. So, let's connect the terminal. If you come this area, you will find OC1A, B, and C. This is the comparison match output of timer counter 1. Please come here and enter 1, 2, 3 with the terminal as default. Here, you can first select motor underscore A, then motor underscore B, and then motor underscore A. You can choose. Next, we will connect the wires. In this way, the three comparison match outputs are connected, but motor underscore B is not connected at the end. I have OC1C. You need to do OC3A. If you look at OC3A, it is number 3 in port. Pin number 3 is 5. You have to do it on pin 5, 5. So get a terminal. You can move it by rotating it. Enlarge the OC3A and connect it to the OC3A, and if you select motor underscore B as the label and edit it, the connection will be established. So, logically, OC1 ampere, B, C, OC3 amperes will be connected to pins 2, 7, 9, and 10 of the L293D motor driver. I made a mistake. If you look here, the enable pin is pin 9. So it should be connected this region. I made a mistake. I made the connection completely wrong. Select it and move it here. The enable pin must be connected this part. The enable pin should look like this. This is normal. I almost made a mistake. Each enable pin is on this side. Insert 5 volts into the enable on pins 1 and 9. Motor A and B are inserted into pins 10 and 15, respectively. Then, enable is set to pins 1 and 9, and motor A and B are set to pins 2 and 7, respectively. Now if we work up to this point, we have designed the DC motor. Now, I designed it up to this point, and now, let's drive the DC motor. Let's copy the DC motor section from a code file. We will test with a simple code that does not use PWM control, but only on-off control. Please compile. You can use Control F9 or select the icon build all project file here. Let's run it. Then you can see the current flow, as you can see. So you can see that the motor is rotating. This concludes the practice of driving the DC motor up to the actual firmware. Now, let's do ADC. ADC doesn't have any special objects to add. As you can see, we will add a variable resistor to ports 0 and ADC 0 to see how the ADC value changes. So, let's move a little bit this way. I moved to port 0. ADC 0. Channel 0 side. You can move here and register a variable resistor. What is a variable resistor? It was pot. You can register like this by pressing pot, so put it here. Next, we will set the capacity value to 1K. Instead of 1K, I won't change it to 1K. You can say 5K. You can give it 10K, or you can give it 2K. There won't be any major problems. Let's copy one VCC. Copy using copy to clipboard and paste from clipboard. I need to make a copy of the ground as well. Copy to clipboard. Paste from clipboard. To copy it. And then I'm going to rotate this part. Select the variable resistor section and press R to rotate it. Let's connect now. There is one thing you need to be careful of when using ADC. We need to register the reference voltage, but we will only use the AVCC reference voltage. Therefore, without applying the voltage to the RF side, you just need to put 5 volts into the AVCC of pin 64, which is the reference voltage of the ADC. So, you can copy 5 volt to clipboard and paste from clipboard to insert 5 volt. If you input this here, the reference voltage for comparison has been set. Now, we will check whether the ADC value is converted and displayed on the LCD by inserting the firmware and adjusting the variable resistor. I will take the ADC test code using a variable resistor from the code as is. The code is a bit long. This is an example of taking the ADC test part and using Control A and then Control V to display the ADC value. As you can see, the LCD was used as PORTC. So what do you think? When you come to the project, go to Configure, go to Project, go to Configure and define it when using the LCD. I went to see compilers libraries and said that enable alphanumeric LCD support in alphanumeric LCD must be unchecked. Please press OK. Let's compile it. Control F9. Cancel. Let's try running it. Because it's in the exact center right now, you can see ADC values from 0 to 1023 to 512 for a total of 1024. Let's lower the resistance value. So what if the ADC value decreases? I'll upload it again. The ADC value increases up to 1023. So since it is an ADC with 10-bit resolution, check the value change from 0 to 1023. Now, stop the simulator at this point. I missed one, so I'll put ADC here. Here, we will enter a graphic object called ADC. Select it, right-click, and select Copy to Clipboard. I will use Paste from Clipboard. I should do it here. Double-click and go in and edit it to ADC. I will modify it to ADC. Now let's do one final simulation of RS232 UART communication. To use RS232, you need to register 2 terminals. If you look here, it's called Virtual Instrument Mode. Go to Virtual Instrument Mode. There is a virtual terminal. After clicking this, we will register too. In addition, the first and second are registered here. The RX pin RXD and TXD must be connected to the microprocessor by crossing each other. So, here PDI RXD 0 P0 so RX must be connected to TX. Therefore this can be connected to TX. Then TXD 0 King B connected to RXD like this. Then right-click and write something here TX. Here you can write RX. Now they intersect and connect each other. We will register it here as RS232. I will copy to clipboard, paste from clipboard, and modify it to say RS232. Okay, if you get to this point, that's it. Now let's install the firmware and check whether the terminal operates normally. Come to code. Now finally, let's run the code called RS232 test as is. Just Control-C the entire thing and import it into CodeVision, the function that initializes the register by using Control-A and then Control-V. Is exactly 62 lines long. I'm going to press Control F9. Please press cancel. Let's run the simulator. Look at it now. When you run it for the first time, the terminals are loaded automatically. It is shown. I'll close it. Let's stop the simulator again. If I run the simulator again after stopping, there's no response. At this time, don't panic. Just go to debug and artificially load this terminal. You can load it like this. And it displays 1, 2, 3, 4, 5. Normally, 1, 2, 3, 5 appears. And if you enter here, you will see B. Let's enable the echo function. Come to TX and become an echo-typed character. If you check here, now. If you put B, B will be displayed and C will look like this. You have confirmed that the RX part and TX are running normally. Please do not be confused by this part. You just need to know that if the terminal doesn't open, you have to go to debug and open the terminal artificially. Now, let's stop the simulator from running. If you make it this far, you have completed the practice up to RS232. So now, you can use the simulator I made in the lab. I teach. You can download the firmware here. Through the simulator, we have created an environment where you can learn without a kit. You can make it yourself and practice it like this. I told you that I have also attached the file I have already created as a result to the video link. So for those of you who haven't been able to follow this part, this is the file after you have licensed the Proteus software. Use this file called Proteus for AngelRo.pdspRJ. You can practice various firmware like this by just loading this file. Since the simulator has been created, you can use this file. Thank you for listening to the Proteus lecture for a long time.